All right, today we are diving into something really cool, a new kind of geometry. But we're not talking about the geometry of space. We're talking about the geometry of ideas themselves. We are literally going to draw a map of the landscape of truth. And to get started, I've got a very weird question for you.
So just think about that for a second. How far is the number 2 from pi? Now, I know your first thought is probably about 1.14, right? But that's not what we're talking about today. We're not thinking about a simple number line.
You see, the real distance, the one we're going to explore, isn't measured in units. It's measured in information. It's all about the complexity, the amount of logical work you have to do to get from one of these ideas to the other. Let's see how that actually works.
Okay, so the first big shift we need to make is to stop thinking about logic as just this rigid set of true or false statements. Instead, I want you to picture it as a vast, sprawling landscape, a place that has terrain, that has landmarks, and crucially, has distances between those landmarks.
So how in the world do you measure distance in a landscape of ideas? Well, the key is this concept called Kolmogorov complexity. The best way to think about it is like this. The distance between two ideas is just the length of the shortest possible recipe, the shortest computer program that can turn one idea into the other. If you need a really long, complicated recipe, well, those two ideas are very far.
And this quote just nails the whole point. We're getting away from a simple true or false. That's not the interesting question anymore. Now we can ask, how far is this statement from that foundational belief? We're creating this beautiful, graded, totally measurable relationship between all these different kinds of truths.
Now, if logic really is a landscape, what does it, look like? This is where things get super interesting visually. We're about to take this really abstract idea of a logical manifold and make it something you can actually see.
So the best way to visualize this whole thing is something called a Poincaré disk. I want you to picture a circular map. The center of the map, that's familiar territory, simple ideas. But as you move out toward the edge of the circle, the terrain gets unbelievably compressed. A tiny little step way out near the edge could be like crossing a huge logical distance. That's the mind-bending nature of this hyperbolic geometry. So let's break down the legend for this map. The anchors, those are our foundational axioms. They're the solid ground we're standing on. As you travel out towards the edges, you get into these regions of way higher complexity, where truths are just packed together super densely. And all the space in between? That's described as a fractal foam of statements that are kind of independent or maybe only partially true from where you started.
Okay, so we've got ourselves a map. What does any good map need? The coordinate system, right? We need a way to actually pinpoint the exact location of any given truth on this crazy logical landscape.
Now, the vertical axis, it's not a smooth line. It's more like a ladder. Think of level 0 as your basic set of rules, your starting universe. Level 1 is like taking a step up the ladder and looking down. From here, you can see truths about level 0 that were impossible to see when you were inside it. You can solve its paradoxes. And every step you take up that ladder gives you an even more powerful meta viewpoint.
And what about the flat surface of the map, the horizontal coordinates? Well, here we've got two different kinds of locations. First, you have rational coordinates. These are the truths you can reach with a standard proof, taking one logical step after another. You can literally walk right up to them. But then you have the irrational coordinates. These are things like Gödel's famous G statement, these wild truths that you know exist. You even know their address on the map, but you can't just walk there. You have to kind of sneak up on them with approximations, or leap up to a higher level on that vertical ladder to actually see them clearly.
All right, this is it. We have our map, we have our coordinate system. It is time to open up the Surveyor's Toolkit and look at the actual computable formula that makes this whole map practical, the thing that lets us really calculate the distance between any 2 points.
So this total distance, or cost, is made up of 3 parts. The first one is the description cost. This is basically asking, how complicated is the tool you're using to begin with? A really simple idea like just chopping off the end of a decimal is cheap. It's easy to describe. A really complex mathematical series, well, that's going to have a higher description cost.
Next up is the second part, the precision cost. Think of this like your resource budget. If your method needs to use absolutely massive numbers, technically really large denominators, to get close to an answer, it's going to pay a high price here. It's basically a penalty for being inefficient, for using brute force. And the final piece of the puzzle is the one that's probably the most intuitive, the approximation error. This is just what it sounds like. It's the penalty for being wrong. How far is your answer from the actual target? The bigger that gap, the higher the cost. Simple as that. So you put all three of those costs together, and what you get is the cost-weighted distance. The whole goal is to find the most efficient path to a truth. It's not just about being accurate, it's about finding that perfect balance. The axiom that gives you the most accuracy for the least amount of complexity and resource cost. It's about finding the most elegant route.
So, let's bring this all back home. We started with that weird question, and now, finally, we have the tools to give it a real answer. Let's actually calculate the informational distance to pi.
Okay, check out this comparison. Let's try two different ways to get to pi. First, just chopping off the decimal. Super simple idea, right? So it has a very low description cost. But its precision cost is insane because the numbers it needs gets huge fast. So the total result? It's actually informationally very far away from pi. But now look at something like the Leibniz formula. It's a more complex idea, so its description cost is higher. But it's way more efficient, so its precision cost is much, much lower. The result? It is informationally way closer to pi.
So here's the absolute crucial point to take away from this. This metric, this way of measuring distance, doesn't just reward the simplest idea. It rewards elegance. It rewards efficiency. The best axiom, the one that's closest to a truth, is the one that has the most efficient balance between its own complexity and its power to get you an answer.
All right, let's do a quick recap of this whole journey. We started by picturing truth not as a boring list of facts, but as this dynamic, geometric landscape. We figured out that the distance in this landscape is measured by information complexity. We learned we can actually visualize this strange space as a hyperbolic map. And, most importantly, we now have a real formula to get out there and start charting it.
What this framework really gives us at the end of the day is this profound shift in how we think about knowledge. Like the source material says, we've basically transformed our understanding from a dusty collection of facts into this rich, complex, and totally navigatable world.
And that leaves us with one last, really tantalizing thought. This whole thing is a tool for mapping abstract concepts. So, if we can now actually chart the landscape of pure mathematical logic, what other invisible worlds are out there, just waiting for us to find a new kind of map?